Hi folks, welcome back to Physics with Captain Rod. I just wanted to start that one out with a little mood music. Alright, so I'm making this video here to help you out or get you started on numbers 17, 19, and 21. These are in chapter 2 of your OER textbook. So, alright, let's talk about 17. Alright, so it says, let's see, Dr. John Paul, U.S. Air Officer, was on a rocket sled accelerating from rest to 282 meters per second in 5 seconds and was brought back to rest in 1.4 seconds. Calculate his acceleration and deceleration expressed in multiples of g. Okay, so I want to talk a little bit here about the term decelerate and why physics people don't like that term, but I'll save that for when appropriate. First thing you should do with all of these problems is draw yourself a picture. All right, so we got some sort of rocket sled. I'm going to take the time here to actually do this. All right. Oops. And presumably this is, a horizontal type of motion. This probably occurred on a frozen lake or something like that. And shrink this down even further. All right. And I like to start these again with a motion diagram. Remember what the motion diagram would look like. It would look something like this. These are like snapshots in time of this rocket accelerating. Right? So maybe here's my kind of motion diagram for the first 5 seconds. Okay, so I'm going to put that in a picture too here. Here's my delta t, 5 seconds. Then the rocket was brought to rest really quickly. So I'm going to kind of continue the motion diagram. Okay. And this occurred over a very small time frame, listed in the problem. 1.4 seconds. All right. So it's important. It's very important to realize, when is the velocity increasing? When is it decreasing? So in the first part of the picture here, the velocity is increasing. All right. So these are velocity vectors. The acceleration, I'm going to draw these vectors in red. The acceleration is this way. I'm going to assume constant. It doesn't necessarily say that, I think, in the problem, but it's a very common assumption to make. Now, in the second part of the trip, like from this time on, now the velocity is decreasing rather quickly. Right? And the acceleration is now in the opposite direction. Now, you notice I drew these arrows a lot larger. That's because this thing went from 0 to some time, or to some speed in 5 seconds. It was brought from that speed to 0 in 1.4 seconds. The acceleration had to be larger in magnitude during the second part of the trip. So this is a relatively short problem, but I still encourage you to draw these pictures because they're very important for understanding how, what the motion's looking like. You don't have to actually draw a little rocket ship. Everybody's seen in class what I do is I usually, maybe draw one picture and then just use like a dot to represent the object would be perfectly fine. Now, next, draw a graph that describes the motion of this. And the velocity graph tends to be the most useful. It's a really good thing to do. Once you have the velocity graph drawn correctly for about any of these problems, you're just about home free. Then it's just a matter of using concepts of slope and area to solve these problems. So this rocket starts from rest, right? So that's going to give you a data point here at t equals 0. The velocity would be 0. 5 seconds later, the velocity is a value, and that's given in the problem. I'm not even going to write it down here. You can get it. And what that'll allow us to do is put another data point here, 5 seconds, and put that, whatever that number is. If we assume constant acceleration, that allows us to do something like this. Now, 1.4 seconds later, the rocket isn't moving anymore. It's stopped. So here's 5, and then 1.4 is just barely over a little bit, and the time would now be 6.4 seconds because we're starting at 5 and adding 1.4. So the velocity decreased over this region. So when the problem says to find the acceleration and the deceleration, what they're referring to is this. You're going to find the acceleration during the first half of the trip from the slope of this line, and you're going to get a positive value. You can get the acceleration from the second half of the trip from the slope of this line, and notice that this has negative slope. You're going to get a negative value. Now let me chat a little bit about that deceleration term. All right, acceleration is a vector quantity, and whether it's positive or negative, it doesn't have to do with speeding up or slowing down directly. It has to do with right or left, basically, or up or down. It has to do with direction. The term decelerate shows up. Basically, people use that term whenever your acceleration is in the opposite direction of the velocity, which would have a result of slowing things down. It's not a real good scientific term. A lot of people, including myself, do not like the term accelerate. Right? If your velocity vector in this example is to the right, and we decide to call right positive, which is a logical thing to do in this problem, then any acceleration to the right would result in this object speeding up and would be considered positive in this set of coordinates. Any acceleration to the left would result in the velocity decreasing, and these accelerations would be considered negative in this set of coordinates. But the reason they'd be considered negative is not directly because the rocket's slowing down. It's because the acceleration points left and we're doing right positive. And I'd like to further take that just a little bit further. Imagine that this rocket slowed down not by applying some sort of brakes, but maybe it's got a rocket in the front of it or something, which, blasts off stuff in this direction. Perhaps it's got another engine up front. If that engine fires, slows the rocket down to a stop, but that engine keeps firing, the rocket will now start accelerating, the rocket will continue accelerating to the left. This engine would be pushing the rocket in this direction. And while the rocket is moving to the right, the velocity would be decreasing and the acceleration would be in the direction shown. But eventually the rocket would stop, and if you keep that engine on, then the rocket will start moving to the left and that velocity will start increasing. It's important to note that the acceleration would not change sign. It would still be to the left and therefore negative in this coordinate system, even though the rocket would be speeding up. So anyway, the textbook uses the term decelerate. Physics people like me, we don't like the term decelerate, but what they're referring to when you see the word deceleration, they're referring to a situation where the acceleration and the velocity are in opposite directions, and therefore the velocity would decrease. So anyway, long story short, slope of the line in this region will get you the acceleration during the first part of the trip. Slope of the line in this region will get you the acceleration in the second part of the trip. Let's call 17 done. All right, and we'll move on to 19. Let me get rid of this stuff here. All right, so 19. What does it say here? An intercontinental ballistic missile goes from rest to 6.5 kilometers per second. So I would write down our information here. Now it says rest, that's the initial velocity, so I might call something like v sub o 0 meter per second. That's a common way to denote an initial velocity. We're given some sort of final velocity. I'm going to call that v final, 6.5 kilometers per second. We're also given a delta t, 60 seconds. All right, so I'm going to go ahead and get my rocket back here. Shrink it down smaller than that. Should always start these problems with some sort of picture that describes the problem. So here we have a rocket, starts presumably from the ground. All right. Motion diagram, another good thing to put in the problem. This time I'm just going to use the dot to represent the rocket, but this rocket would be speeding up, so the motion diagram is looking something like this. The velocity of the rocket starts out small, but it's going to get bigger with time. right? Eventually you're going to have a really big velocity. The acceleration of the rocket is this way. I'm going to assume constant acceleration. I don't think it directly says that in the problem, but it's a very common assumption to make. Now, the way I want you to analyze these problems: 1, start with a good picture. 2, draw a velocity graph. Once you have a velocity graph, things typically fall in place pretty fast. And here we have data points to just use. At t equals 0, the rocket has a velocity of 0. So just put that point on the graph. 60 seconds later, the velocity is 6.5 kilometers per second. So on our graph here, 60, 6.5. Now, you notice I pretty, kind of casually just, put this wherever. That's perfectly fine. You are free to set a scale. Now, at this point in this problem, I've kind of set a scale. This distance on the graph is representing 6.5 kilometers per second. So 3 kilometers per second would be, a little less than halfway, and 12 would be, right about here, and so forth. And connect the dots. Now, if we assume constant acceleration, and remember acceleration is the slope of a velocity graph, that would be indicating that this is a linear type of function. Now just use concepts of slope and area to solve this thing. If it asks for the acceleration, that's the slope of the line between these 2 points. Now, if we do that, however, let's consider units. This is in kilometer per second, and this is in seconds. So if we do the slope, you're going to get kilometer per second per second. You could also just write this in meter per second. 6.5 kilometer per second is 6,500 meter per second. And I think I'd probably just use this value to when you calculate the slope. And let's see if there's anything more about that problem. What's the average acceleration? Okay, where it says in multiples of g, here's what they mean by that. Gravitational acceleration is approximately 9.8 meter per second squared. I like to round that to 10, approximately 10 meter per second squared for rough calculations. So any acceleration that's around 10 is called a 1g acceleration. An acceleration of 20 meter per second, you see how that's double, it would be referred to as a 2g acceleration. 50 meter per second, I'm sorry, and I'm saying meter per second or meter per second squared. A 50 meter per second squared acceleration is about a 5g acceleration, and so forth. So you take your acceleration, divide it by 10, or more appropriately, you should really divide it by 9.8, and that will tell you how many multiples of gravitational acceleration it is. So now, I don't think it asks for it in the problem, but I would like to point out that if we wanted to know how high that rocket was at this time, this area right here would tell us that. So that's probably enough for number 19. I'm going to just call that done. Get rid of all of this stuff, and we'll talk about the next one. All right, 21. What does that look like? So a well-thrown ball caught in a well-padded mitt. Oh, there's that ugly term again, deceleration. Now this is given in the problem that we have an acceleration of 2.1 times 10 to the 4th meter per second squared. Now, whether this is plus or minus has no meaning yet because I've not defined a set of coordinates or a set of directions. So for now, we'll just leave it like this, or maybe we'll say the magnitude is equal to this definitively, and we'll talk about plus or minus signs here in a minute. The problem is about a baseball, so I'm just going to sketch a quick picture of the ball. And the ball's moving along, it's got a velocity vector that's some value. Then what happens is the ball comes in contact with a catcher's mitt. So I'm going to kind of draw that. Imagine that, like, here's the surface of my catcher mitt, and we're going to imagine that catcher mitt's kind of wide. The ball would deform that mitt and stop over some distance. So I'm going to draw another picture of the ball where the ball has moved some small distance. I'm going to call that a delta x. And in this picture, the velocity would be 0. So what's happening is the ball is going from a relatively high velocity to a velocity of 0. What you want to do here, sketch a velocity graph. Right, velocity against time. And if I define this way as positive, then the initial velocity is some positive number. Now I don't know that that's even given in the problem. Let me take a look. It's not. What we're given is the acceleration and a time. So this is an unknown. The initial velocity of the ball, unknown. So I'm just going to put v sub o. But that doesn't stop me from putting a point on the graph. I do know it's moving to the right. That's positive in the set of coordinates we decided to work in. Some short time later, the ball is stopped, t, and therefore has a velocity of 0. We'll go ahead and assume constant acceleration. Here's a delta t. Now, by the way, once we've made this assumption right positive, and the ball is slowing down, therefore the acceleration is in the opposite direction of the velocity, now we can say, all right, we're going to use a negative number for that acceleration. But it's not until you define this that you can start talking about this. Now, slope and area. Write an equation for the slope of this line, because acceleration, remember how it's calculated, change in velocity over change in time. Anything that you calculate that's change in something over change in something is a slope. This is an unknown. When I go from here to here, the rise, if you will, would be minus v sub o over the delta t is given, and so is the acceleration. So you should be able to use this equation here to solve for v sub o. So that should get those 3 problems done. This video is getting a little bit on the long side here, so I hope that these help. Have a great day.